So today I want to talk about survival analysis with a Python package called Lifelines. A little bit about me first. I'm a data analyst at Autodesk. You can find me and my blog related information at roundingaverage.dev. Enjoy coffee, learning, and running near the beach as well. And some notes. This presentation doesn't reflect any work or material representative of where I work at, but then also I'm not a core contributor of Lifeline project, rather just a user. And yeah, just stay well through these times and stay healthy. Hope you and your families are well. That includes just like social distancing, wearing masks, washing hands, and other things to make y'all safe. So what we'll be talking about today is, again, survival analysis. What is survival analysis, first of all? Survival analysis is used to estimate the time of an event for some sample or population, and then it came in from origination in like medical research to understand the probability of time of death for an event throughout time. But the summary of it is survival analysis attempts to answer the questions such as, what is the proportion of a population which will survive past a certain time? So why should I consider survival analysis? Let's take a look at a customer churn scenario, though I just mentioned that there was its origination was from medical research. Say we have a database of Insta2U customers with their subscriptions. Insta2U is a fake delivery service that delivers 2U albums. This database also has like some additional information associated to the customer. You can see this right here. For example, something like tenure, maybe even like some financial related information and churn. Because we have the start and end date of these tenures of these customers and their subscriptions, we can observe the event of interest, that is the customer's life expectancies for a churn over time t, which can see in this visualization right here. And this is foreseeing what's going to be implemented in the package that we're going to use soon. Another recent example, actually, I was looking in the Twitter sphere and I noticed a conversation from a individual that does a lot of research within the current situation we're going through right now. But I thought, it was recent, relevant, and also empowers the use of survival analysis, which is this individual saw in the study that the study claimed that 80% of mortalities had occurred if an individual or individuals were placed in the ICU with a ventilator. However, that wasn't the case because in the study, it didn't consider those that were still alive and still in critical condition and in the hospital, but didn't factor into that denominator to give that percentage of the mortality, which provides a false depiction. So within that, what are the special properties of survival analysis that enables the correctiveness of like that type of analysis in the recent example, but also in that customer churn example? Censoring. So with censoring, we have the ability to say at some point in time t, if those individuals are of the events that they continue to live on or like they live on past like certain that point in time t, in this case, in that horizontal line, we can see that value 50, then there can be right censoring occurring. And then also to that, there's also left censoring that is provided in survival analysis. Yeah, so we can also, for that original graph I showed earlier, we show the probabilities over time and estimations, and that's through the survival function. And for the survival function, has like some set of properties like as t goes on throughout time, that probability is decreasing. That being said, the survival function s of t right here is non-increasing. And yeah, since it's a probability, it ranges between that value of 0 and 1. And then I'm going to bring about that same visualization again, and we'll go into that soon. There's also regression that can be provided in survival analysis. However, it's not the traditional regression you would think of, where like in traditional linear regression, for example, like you would estimate a certain value, quantitative value or categorical value. And what this regression does in survival analysis, we try to compare between like covariates or like those variables to their duration, which was that time t. And there are some like models available within regression that allows for that. There's, for example, the Cox proportional hazard model, Eland's additive, and exponential. Something I won't get into in this discussion, but it's good to note now. So you're like, okay, Raul, I'm convinced. How can we implement this? We can use Lifelines. Lifelines is a Python package for survival analysis, and it was developed by Cam Davidson Pilon during his time as director of decision science at Shopify. That, though now he is currently pursuing something in academia, but also maintaining this Python package and some other Python packages as well. Some resources to that are like available at the end if you're like interested in seeing what they are. The benefits of Lifelines is scikit-learn friendliness. It's built on top of pandas, so you get that like convenient coding experience like you would in like in pandas in Python, if you're familiar with that package. Handles this this thing I mentioned about left and right censoring, and some other items. But I'm curious, how is that survival function S of t estimated? It's done through the Kaplan-Meier estimate. And then the way that this calculation goes within the Lifelines package is the estimated survival function is calculated through a multiplication over some like time t, this symbol right here. And for every time t, we take a ratio of like the number of individuals that are subject to the risk at that point in time minus the deaths or whatever happened at that occurrence. It doesn't have to be death. That d right there divided by the number of subjects subjected to like risk at that time t, and then that multiplication occurs that there. I want to show like a visual example, but I'll show like a resulting table using Lifelines. And let's now go back into that customer churn example or that non-increasing visualization we saw earlier. We can actually see it being applied now. So here we import the Lifelines Kaplan-Meier fitter function and implement that. And you can see right here, conveniently, we do a dot fit as a method and add in certain parameters like duration in our data set. Originally, like we add that churn as our duration, and the event observer we're interested in seeing is churn. And from there, we get the resulting visualization that kind of been showing earlier, like not ad nauseum, but a few times through this method right here, dot plot. And we're also showing the confidence interval as well, respective to that. And you can see this like band go throughout time in that like light shade blue. Yeah, and there's also some additional feature functionalities that you can also do conveniently, like call a method called event table. So you can see like a table of the what has occurred, kind of like equivalent to that visual depiction that we just saw just now. And then also you can see like that confidence interval band, the quantitativeness of it. We can actually see the numbers of it as opposed to like the visual light shade blue representation that we're seeing now. So what about regression? Again, unfortunately, with that being said, thank you.
That's great. Does anyone have any questions if they want to raise their hands or ask a Q&A? There's a message in Q&A. What kinds of problems have you used this package on recently?
Yeah, it's a good question. So though I didn't say I'm not showing anything related to Autodesk, but I've implemented it at Autodesk right now, and with another teammate, just going about understanding the durations of certain segmented groups of customers. But yeah, other than that, it's pretty much it. And then also like kind of personally too, like in this publicly available data set that we have now, it's also documented as well. So you can also reproduce this as well. And it'll be available on my website at rollingaverage.dev.
We have another question, another hand raised. Stephen, go ahead.
Yeah, hi, Raul. So on the first slide, when you defined survival analysis, you didn't explicitly say, but it's transitioning between multiple states, right? And there can be more than, simply dead and healthy, or for a machine, functioning and malfunctioning. How many different state transitions do you generally work with? How many can this package handle?
That's a good question. It's something I haven't fully gone into, but something I can circle back to, like answer separately through something like individual investigation.
Sure. Yeah. I mean, the canonical example for cancer patients is, you have, healthy, dead, and recovered. But the point being that somebody who's had a condition at once is maybe more susceptible in the future. So, state dependent.
Yeah.
Thanks.
I think there was a question about what are N sub I and D sub I in the formula.
Yeah. So yeah, that's a good question. So I was noticing the syntax of it. I think I would have to like edit it and like make it like as of a T. I got to look again. I was doing some like last quick minute edits, so that can be an error there, but it would have been like for like a value T instead of like I have to like double check that.
Thanks. So this is a open source tool called Data Workspaces. It's a tool for managing data science projects. And I've done this with Rupat Majumdar, who's at the Max Planck Institute for Software Systems over in Germany. And we have a website for our project. It's at dataworkspaces.ai. So kind of the real quick overview is that why do we have this is that if you're doing a data science project, it can be very painful to track what you're doing, reproduce your results, and collaborate. And so we'll see how we can solve that. And so Data Workspaces is a Python-based open source layer on top of Git. And what it provides is ways to kind of organize your work across multiple physical virtual locations, capturing different kinds of data, and we'll see that, and kind of going backwards and forward in time, and supporting decentralized collaboration. And it's for people who are doing data science or bioinformatics or other projects where you have experiments involving data. Okay, so so these are some of the pain points that we're trying to address. The first one is that project data is not centralized. You might think you have like if you're doing a simple project, maybe you're doing on a notebook and you're on your laptop. When you get into much larger projects, you have complicated workflows and things going on, large data that you'll never be able to fit in a laptop or in a Git repo, and external resources, and people are getting results on their own individual machines, and you need to combine them together somehow. So it can get complicated. And traditional kind of configuration management or source control systems like Git are not really kind of optimized for that use case. The second pain point is reproducibility. So, I mean, obviously, if you're a climate scientist, then you need to kind of justify what you're doing every step along the way. But even if you're kind of doing normal data science, you want to be able to say, go back in time and kind of take exactly where you were at and tweak a few parameters and see, basically control for just control for everything other than the experimental parameters. And the other thing is, maybe in 6 months, you come back to your project and you want to kind of get it going again and reproduce what you were doing before. And finding collaboration, this is about getting your environment running on someone else's machine, and ideally in less than an hour, and kind of sharing code and results as you're going along. And so this slide is showing, this was kind of a motivating project. We were working on a data science project to analyze emails, and it's probably a medium complexity, I would say. And it's got like some about 4 or 5 steps here you can see, and we're kind of extracting content out of the email using natural language processing. We're building a graph database so that we can analyze conversations, then eventually doing feature extraction and machine learning. And each of these steps takes some amount of time, anywhere from like a couple minutes to 40 minutes or so. And they have a number of parameters, and these parameters are not just Booleans, but they can have multiple values. So you can have hundreds of combinations of things that you might be possibly running. And there were like 5 data sets. And what I found is like, whereas we're running the experiments, you just kind of get lost in what you did. Did I try this? Did I not try this? Or you get like, I got like, I'm 5% worse than I was yesterday. And is that because I broke something in the code? Is it because I have a parameter different somewhere that I didn't realize? Or is it, part of the natural sampling, that I'm doing? So these were kind of the problems that motivated the project. So our solution is called Data Workspaces. And the idea is to bring together kind of the different parts of your project in one meta repository. And this meta repository, this meta repository is basically a Git repository, and it has it has references to the other places where you have your data and code. So and we kind of organize, this can be both local and remote, and we kind of organize it by the type of data, which can be like your source data, intermediate data that you generate somewhere along the way, your results, and your code. And when we're doing this, we kind of call these things resources, and a resource is kind of a bunch of data for one purpose that's sitting in one physical location. And so what we can do then is we can kind of snapshot and restore this workspace or individual resources. And that lets you kind of do time traveling and reproduce and go back to kind of previous experiments. And we automatically capture kind of a data lineage as well as your results. So this is an example of what kind of picture of what a workspace might look like. And this is a simple project. We have 3 resources here. We have one is source data, and this is an external Git repository. We have some Jupyter notebooks, and then we have the results we're going to generate. And so we kind of we want to model all 3 separately in this system, and it will actually generate this ourselves. So this is showing a slightly more complicated one. In this case, we're doing some climate analysis on ocean buoys, and the data is coming from the government, and it's been collected since the 1970s. It's, kind of the format has changed over time. In the old days, they were using 2-digit years. Now they're using 4-digit years. They use 999 to represent missing data. There's all kinds of weird things about it. So what we want to do is do like a pre-processing step and clean up all that data and basically hundreds of files, and then generate some cleaner data. And then from there, we're going to do our analysis. So this is kind of a slightly more complicated workflow, as you can see. And they can obviously get arbitrarily complicated. But in this case, we're going to use we have kind of all 4 types of these resources. We have source data, code, intermediate data, and results. Okay, and so this is what, as an individual scientist or data scientist, what your workflow might look like using the tool initially. And so these blue boxes are commands. So it has a command line interface, which is kind of similar to Git's. And these commands are roughly analogous to Git's, but they're kind of a higher level. So you can see there's a init, so that's to create a new workspace. Add will add, is not to add individual files, but to add resources. Then you can run experiments, review your results. You can go back and forth as many times as you want. You can take snapshots of the entire workspace. And then you can continue, take more snapshots. At any point in time, you can restore to a prior state. Okay, so we can also do experiment tracking. So one thing is, in our results resources, rather than kind of overwrite in typical Git repository, if you copy something, you're overwriting the previous version of the file, and it's maintaining the version history. But for kind of results, you may want to kind of keep all those together as separate. So what we do is we kind of basically, when we take a snapshot, we take what's in the results and move it off to a separate subdirectory. That way they're all off in one place. And we also, there's a special file. If you generate this, we'll kind of use it in our reporting. And then we have an API in Python for data lineage, fairly simple, but basically tracking the steps of each step you do. And then we kind of tie it in with the snapshots where we have hashes of each of the resources. And then finally, there's API integration. So integration with scikit-learn and TensorFlow. And these basically allow you to track this lineage automatically, not have to do much annotation to your code. Okay, and then we have some reports. So this is showing you a couple examples. So one is a history of snapshots, and the other, this is showing you a lineage graph where we're kind of taking a number of data sources, creating intermediate data and the final results. And these edges are basically the commands or the steps that were used to run it. So I'm going to next show a demo. Is there any questions right now?
It looks like there is a question that says, is this package open source? Where is it available? And how does it compare to the alternatives, for example, Apache Camel?
Okay. Okay, and I'm seeing a few more questions. So it is open source. If you go to dataworkspaces.ai, and there'll be a link at the end, or I can put that in the chat, I guess.
We'll just answer them for you as well. We'll help handle some of that for you.
Okay, so anyway, it's dataworkspaces.ai, and there's a GitHub. It's all up on GitHub. It's under Apache license. And I'm not sure. So there's other things out there, and so I guess, and there's some things that there's something called DVC, I believe, which is kind of more also kind of a layer on top of Git. In our case, we're trying to kind of be a little more flexible in handling multiple things, multiple different resources that are not all in one repo. And there's other things that are kind of tracking lineage more in the Hadoop ecosystem. And so we're not really kind of focused on that, but more on the data science experiments. Although, I mean, kind of one of my kind of medium-term goals for the project is to be able to import lineage from maybe those other systems, so that if you have like a big data environment with pre-processing, you could kind of, if it has lineage tracking, we could import that data into our graph. Chris was asking, is there any reporting across experiments in aggregate? So you'll see in a minute, there's some reports that we can do about showing you kind of the metrics of things of different experiments and whether they were better or worse. Actually, I can probably just show you real quickly what that. So I don't know if you see, so like this is showing you a report across a number of experiments, and you can see these are snapshots that were taken at the end of the experiment. These are, kind of a bunch of the metrics, and you can see these various parameters, and it's kind of giving you a heat map of which ones were better or worse. So you can do that, and I mean, there's other kinds of reports that can be built on top of this, and we're kind of just scratching the surface so far on what we can do with that. Let's see here. Now let's see, Q&A. So okay, and then can we handle terabytes of data? So we don't. So the system. It's not going to store all the data per se, but one of the things it has is a concept of a resource, and that's an extensible API. So we have a resource for a Git repository, a resource for local files. You can have resources for S3 buckets, things like that. And so the data would still be wherever it is, and the resource API just needs to provide us some way to give us basically a hash representing the current state of the resource. And so in that case, and one thing we have in terms of and if it's binary, that's fine. One thing we have integration with Git LFS, so that if it is in a Git repository, we can kind of, basically it can manage kind of larger files, because Git by default only kind of basically falls apart at 100 megabytes. And yes, we can handle multiple Git repos. In theory, we can handle multiple source control systems. The master repo would still be in Git, but the other source control systems could be whatever. And although the only one we've really implemented so far is Git, and it's sort of based on what our users want. So hopefully that answered kind of that batch of questions. So let me show you a demo.
Jeff, can I ask?
Sure.
Well, I'll wait till the end. Sorry.
If you think it's a good time, it's fine.
Yeah, sorry to interrupt. I'll wait till the end. Thanks.
Okay, now hold on a sec. Okay, so now I'm going to show you a quick demo of the first part of this. So I'm going to create a workspace called demo. Oops. Okay, and now what I'm going to do is I'm going to do a DWS. So DWS is this master command. It's kind of like Git, right? So it has a bunch of options. You can see here all the different options. And that's one thing And speaking of Python, I highly recommend if you're building something like this, there's a library called Click, and it makes it really easy to build these kind of nested command line applications and have all the help. And because basically these are just, most of this stuff is just comments, you know, the doc strings in the code, and it can pull it out automatically. And there's even the ability to generate automatic. So some of the documentation for the command line API is auto-generated. So, which is really cool. So I highly recommend Click. It's on, you know, pip or GitHub and all those things. Okay, so now I'm here. I want to do a DWS init, which is going to create the workspace. And I'm going to also have it create some resources here. So I'm going to have a few resources directly in the main parent repo, one for code and one for results. It's asking me what the name of my machine is. So I will give it that. And so what we have now, if we do like here you can see it's created a subdirectory called code and that one called results. There's a scratch space that never gets kind of synchronized. And this .data, so it's a Git repo. You can see there's a .git and .gitignore, and there's metadata here. So if you look at .data workspace, it has a bunch of metadata there that it's maintaining. And then, okay, so next what I'm gonna do is I'm gonna go and add in a source resource. Hold on. So what I want to do is I'm going to go to GitHub. So this is a Git repo that has my source data. And it's just that if you've heard of the digits, the handwritten digits data set, it's just that. And I have that in a Git repo. So what I'm going to do is I'm going to clone. So that's kind of a standalone Git repo. So I'm going to clone it in here. Okay, and then I'm going to tell Data Workspaces about it. And I'm going to say that it's source data and that it's read-only because we're kind of like assume that this is something that we're not changing, right? Okay, and so we're going to call this resource sklearn digits dataset. So we've created a resource. So there's a report command that has a lot of subcommands, and so one is status, so it can show us what our, oh, of course the font is unfortunately too big for that. Hold on. Hopefully that's still readable, but this is showing you here that you've got 3 different resources. These are the roles, and this is the type, and these are their parameters. So now what I will do real quickly is I'm going to go and add in a Jupyter notebook. Okay, and then okay, so here's a Jupyter notebook with some scikit-learn code, really simple, and it also is going to be importing some things from Data Workspace. It's kind of our integration API. And one thing we have also is an integration with Jupyter. So Jupyter has this thing called magics, and they're basically extra commands you can add. So we've defined some extra commands, and they're pretty similar to the ones that are actually available on the command line. The main difference is they kind of print out a little funnier, nicer, and they're integrated. You don't have to leave the notebook to use them. So we can see some info about our thing. So now I'm going to load the data in. So this is loading it from that resource, and it's just a bunch, which is in scikit-learn is just a dict that has the data's numpy arrays. And so I'm going to do a support vector classifier. It's going to have one hyperparameter that I care about, which is gamma. So we'll define that there. And this is how I'm going to create my model through scikit-learn. Then I'm going to wrap it in this class from Data Workspaces, which is going to, it has the same interface as any predictor in scikit-learn, but it's going to capture all the input data, the parameters of the model, and the results. So that way we don't have to track that ourselves. Okay, and then we split our data set. We're going to do our machine learning, and we got about 70% accuracy. So it wrote to the command line. So if we look in the, so if we look here under results, it's created some files for us. This digits.joblib is the train model, and this results.json is a file containing kind of all the metrics and stuff. And so if we go back here, basically this will pre-print it for us so we can see this is telling us what we ran. This is our notebook, what time it ran, how long it took, kind of all the parameters that were passed to the model. Most of these are defaults other than our gamma. And then we have metrics that it captured, so that's our accuracy, right? And it's multi-class classification, so there's more there. Anyway, so that's the results. So here's a lineage graph. It's really simple in this case. We started with our source data. We ran this command here, digits with magic, and we created our results. And you see here it has these placeholders. So eventually in the data, our like kind of data store, those will be replaced with hashes from the actual resources. And in this case, like the commit hash from the Git repo. But that happens when we actually take the snapshot. So I'm going to take a snapshot now, and a snapshot is kind of like a Git commit. It takes a message and an optional tag, and it generates a hash. So it's run, and this the integration is actually going and saving the notebook to the file system, then running the command in the IPY kernel, and then coming back. So now what we can do is look at the history, and we see we have one experiment. This is the timestamp, the hash, the things, and these are some of the metrics. So it's automatically kind of capturing that for us. And I'll show you, let's say now we want to run a different experiment. We're going to try a different value of gamma. So we can do the same thing. And this time, what do we get? Metrics, we got 97%, so a lot better. And the lineage graph. So we'll take another snapshot, and we're going to call it SVC2. And so there's our snapshot, and we can look at the history there, and we can see, okay, there's our two snapshots. And I'm going to do it one last time here. So let's try one more 0. I mean, I guess typically you would use a grid search for this, but then probably try different kinds of models. Okay, we got 93%, so that's not as good as the last one. But okay. And so I'm going to call this SVC3. And okay, took the snapshot. And I actually want to see a heat map of the different metrics. So here it's kind of showing you the green is the best and the red is the worst. And if this was loss, you know, that's reversed. So, okay, so we've seen here, we've done 3 experiments and we got 3 snapshots. So we've killed that. Now, if I go back here, so I'm back in my workspace. So, and I can run some of these same commands. So I can do DWS report history, and we can see those same information there, hopefully. And then what I'm going to do now is, like, perhaps if you see the last one was, the most recent one is only 94% accuracy. So I want to use the larger one, the better one. So that's SVC2. So I can do a DWS restore as, let's see, SVC2. And so that's going to store the workspace back to that state. And so then if I bring up, see here, go to the code. We bring up our notebook, and we can see now the current state is now with the best result. So we can kind of leave it in that state. And let me kind of close this down. And okay, so so now I've got it in that state. And one thing I can show you is, like, if you look at the results directory, so the results aren't there directly now, they've been moved under snapshots. So you can see there's basically a snapshot subdirectory for each one. And then we look into those, like, they basically have the joblib file, the results file, and this lineage file basically contains the lineage graph for that resource, or basically how it got to generate that resource. So I'm going to go back to the presentation. I guess this may be a good time for questions, if anyone has any right now, before I go on collaboration. Any questions?
There are several questions. I think Karen might want to read them out, or I can.
Go ahead, Glenn. Thanks.
Sure, no worries. So a couple of older questions. This was asked by Clem. Oh, actually, it looks like it just lost one. Sorry about that.
We answered that one, I think.
Oh, okay. So you already answered that one as well. What about, so what was the tool called back a while back? You had a couple of names on a tool. Do you remember which one that one is?
Which tool? The one that I'm talking about tonight, or?
Yes.
It's called Data Workspaces. So
Okay.
if you go to, what is it? Well, you can put it in the chat then, I guess.
Okay, so you'll
Go
put
ahead.
something in chat for Data Workspaces that we'll find that in a bit.
Yeah.
Why? And so Stephen asked, why not contribute this to Apache Camel? Make it handle multiple repos. Seems like there's already a lot of packages for Data Workspace management.
Well, so I'm not familiar with Apache Camel. I mean, I know there's another one that I don't remember what it was called now. There's another one I'm aware of.
Pachyderm.
Oh, well, Pachyderm is a commercial product, I think.
Yeah, I think they have an open source version as well, and there's DVC.
Yeah, so I'm familiar with DVC. Camel, I'm not. There was another one from Apache that's kind of more kind of a big data oriented. So I can look at Apache Camel. I mean, in general, if we can make these different things integrate, that would be great, right? And kind of, like I said, I guess kind of our key value proposition is that we are kind of have this time travel, this snapshot idea tied in with the data lineage, and that it's you self-hosted, right, and built on top of Git, and it's not requiring, you know, like you have to run it in some cloud somewhere.
Perfect. Speaking of time travel, both Dave and it looks like Stephen also wanted to emphasize the same question as well. Is a data workspace suitable to be published with a scientific paper? And will a data workspace continue to work 20 years from today?
Well, that's a...
Well, COBOL's still working, so there's that.
Well, two comments. Actually, this is one kind of like, I have a call at 7 a.m. tomorrow morning for some research institute in Cyprus about that question. They want to use it basically to publish scientific papers. So that's definitely one of the areas of kind of use for us, because again, this is coming out of Max Planck Institute. And I think some of the things, you know, whether it will continue to work, I think that depends on if we can get it more adoption. And then, you know, since it's open source, and hopefully Python 3 is still supported in 20 years, or that it's easy to migrate to Python 4. So, I mean, I guess those would be the other things. And some of the we thought about, you know, doing various kinds of, there's things what I'd like to do to be able to kind of package up. So one thing we can do today is we can take this workspace and create a Docker container for it. So it's actually built, there's a thing called repo to Docker from the Jupyter people, and we've taken that and built a layer on top of that to make it easy to work with data workspaces. And so that's one thing we can do. And then I also kind of like to have some way of kind of automatically generating a bunch of reports, maybe as a LaTeX file that you could kind of include along with it, that would have all the history of experiments and things like that. So that's kind of future work.
For those earlier who were asking for the URL, Jeff has pasted that, https://dataworks.ai. That's also in the Zoom chat that you can find. Yeah. Data Workspaces, if I didn't say that right, .ai. And then the final question I see in front of us is Christopher's asking, hey, Jeff, is it possible for Data Workspaces to automatically snapshot if you're running a set of experiments / parameters, like, for example, grid search?
Yes, in the sense that we have well, there's two ways you could do it. One is there's an API layer So you can call that API, and basically it's a Python call, and it'll do that. The other thing you could do is that you can basically call the command line interface as well. So
okay, that's all the questions that I have.
Okay. So I will talk real quickly about collaboration. So this kind of shows you the collaboration model. And the idea is that we're kind of leveraging kind of Git's power and to synchronize different copies of data. And one of the things we've done is kind of designed our kind of metadata repository to avoid conflicts. So you're not trying to resolve conflicts on the metadata. And for most of the data, there's typically not kind of a conflict, it's additive. But what we can do, so what you can do is there's a publish command, which will basically hook it up with a Git hosting service. So that can be GitHub, GitLab, Bitbucket, whether these are kind of internal to you or the public web. And then from there, then others can basically run a clone, which will pull down everything. And it's kind of a layer over Git clone, but it'll also pull down any kind of repositories or other local state you need. Then you can run experiments, push up things, and then once you push something up, it becomes the others can choose to pull it in when they want to and run their kind of collaborate and add their results too. So that's kind of the idea. And I don't think I'll go through the whole demo on collaboration, but I will kind of show you what kind of the first step. Let's see here. So what I'm going to do, so I haven't integrated yet with the GitHub APIs. At some point, maybe I'll do this. But what you can do is create a repo. So I'll create it, and it can be public or private. So this is just a blank repo here on GitHub. Then I'm going to copy this Git URL, and then I go back to so I'm here in my workspace, and I give it that. And so then it's going to basically set up the remote origin and push everything up. And so we go over here. Let's see. So now you can see it's actually pushed up the repo and everything's there, right? And maybe I can do one more step, which is, let's see. So if I go to another machine, so I'm now on a different machine. I'm going to activate my environment. Okay, so so now what I'm going to do is I'm going to run a clone. So I gave it the same URL. This is the name of the machine. And so now it's also, in addition to bringing down the things, it knows that we have this external Git repo. So it's going to ask us, where do you want to clone it to? And so I can clone it wherever I want on this machine. I'll just pick the default. So now if I go here, I do DWS report history, you can see we have the full history of everything. And it's in the notebook's in the current state, and I'll kind of skip it for now, but you can kind of reproduce the experiments and add new ones and push them up as well. So that's the second demo. So just a little bit about the implementation. So there's kind of at the bottom of this, it has it's relying on Git for kind of file versioning and synchronization. Then there's also this resource API, which is used to kind of extend the thing so it can handle different kinds of data and in different protocols. So, and right now we have, I think, 3. We have Git, we have local files, and we have something called rclone, which is an interface on top of, it's like a synchronization utility on top of a bunch of other things. So you can push it to S3 or to, I know, whatever Azure has and Google has. Then on top of these layers, we have kind of commands and APIs for snapshots and syncing. On top of that, then you have kind of the reporting stuff that kind of looks into the database and builds reports. The lineage API, which you can plug into for your applications or scripts. And then these kits, which are basically using the lineage API and the other APIs to basically make it, to automatically kind of capture that information out of your machine learning library. And then they're off to the side here, we kind of have this deployment piece, which today is really, we can create a Docker container for you. And I mean, eventually maybe we have some way to kind of then push it up to like a Kubernetes cluster or something. I'll mention, so this kind of began as a research project, and so there's actually some theory behind it. And I'll just real briefly touch on it. So part of this theory is about kind of talking about a pipeline execution, and we model it as a directed acyclic graph. And so you have these steps, and they read resources and write to resources. So you can kind of build a graph from that based on the control dependencies and the data. And then, so that gives you a graph. And then we have a concept of a snapshot, and that's basically just talking about the data. And there's kind of two kinds of snapshots that we think about. One is what we call conservative, and that's like, let's say I'm running step S1. Then I want to be, if I want to really be paranoid, what I would do is take a snapshot and get the state of this resource before I run the step. And then after I write my results, and I get that state, right? And then the next step might take this snapshot of its input, compare it to the last one to make sure they matched, and that kind of thing. So that's a conservative snapshot. A post facto snapshot is where you run the whole pipeline, and then at the very end, you snapshot all the resources. And that's what we've implemented. And the key thing is that's a lot more convenient to do and faster, and it's also easier then to go back in time and reproduce past states. And they're equivalent under certain conditions. So basically talking about whether, if you have two things write to the same resource or whatever, you know, if you overwrite things before you take a snapshot, then you would lose information. So we have some checks in the code that can check for that and warn you if that's happening. Okay, so then once we have that, we can kind of define a lineage graph. That's another directed acyclic graph. But now we'll label, so that the states are labeled with, resources are labeled with like the hashes or a certificate. And the steps have their parameters that were passed in, as well as timestamp when they're run and that kind of information. So this is the lineage graph. So we can say from here, we can figure out how to build that result. And we can define things like consistency and reproducibility. And consistency is about, so if you look at, say, this flow here, this R4 transitively depends on R1, and this R1 is used by two steps. And you might run into situations where you do things like this, where I ran R1, ran through here, did the same thing here, but I changed R1 to a new version and ran here. So all of a sudden, this step is depending on two different versions of the same resource. And so that's inconsistent. And so there's certain things like if you want to be able to reproduce something, it needs to have a consistent lineage graph. And so there's some other conditions too. So that's kind of it. So some future plans, integration with PyTorch is like the third main machine learning framework, more reporting, a GUI, and kind of integration with domain-specific tools. The one thing we'd like to focus on, partly for differentiation, is, and also because I think it's an interesting problem, is tools for specific domains. And two that we're kind of interested in right now, one is bioinformatics, because they tend to have complicated workflows and the data is pretty valuable. And the other one is software engineering for ML. So as an example, we're talking to a German industrial automation company. And so as a part of the products they ship, they have machine learning built into them. And they want to know, they want to basically have a record of, you know, how did they train this machine learning? What were the experiments they did? And all that is a part of the thing before they kind of sign off on the thing they're going to ship. And kind of another area that I'm interested in is sort of, if you have different lineage tools for different situations, how do you integrate them together? And can we define some kind of common metadata that can be used across different tools? So I'll kind of end with, so these are some of the resources, the website, which is kind of a place to gather everything. We have our source code on GitHub, read the docs as the documentation, and it's, of course, the Python package.
Could we ask one more question?
Sure, any questions? I'm done now.
Yeah, if anyone else has questions, go ahead and paste them into the Q&A app at the bottom. You can also raise your hands. We will try to answer that as well. The question we have here is, to be sure the code will still run in the distant future, would you need to archive the Python version used and also the libraries used? Is that the future work that you mentioned as a repo to Docker?
Well, so repo to Docker will package up in Workspace as that's from Jupyter, and it will package up we're using it to package up a Workspace as a Docker container. Now, I don't know, you could say whether a Docker container will be usable in 30 years or not. That's a big question. I mean, I could imagine, one of the things we do at least is kind of by doing that process. So if you look at kind of, let's see here, if I can exit slideshow mode, I can show you, like in my case, let's see here, I can show you another one I have. Okay, make this bigger. So you see here, I have this is another workspace I'm working on for a client, and I've got this environment.yml, so that's saying what versions of things they're using. I mean, I could imagine if there's enough demand for something like this, we could look into, saying, okay, you have these versions, let's build some way of archiving that all together. I mean, I think the hard part is, what is that? What do you put that in? Because is that at some point you're, depending on the operating system and all those things, right? Or do you stick it in a virtual machine and hope that the VM images are still relevant in 20 years? But I think at least if you have kind of all these pieces, at least, I mean, one of the things that I think is kind of a more short-term thing is that you can have kind of bit rot in your projects. So we have a project. So this thing here, what you're seeing here is a project that was that I'm working on with a client, and it's been worked on for about 9 months, on and off. And the original guy was a contractor; he's left, and so now me and another guy are doing stuff, and so it's real quickly there's like a bit rot kind of happening where trying to figure out what's there and how it was produced is a challenge. So I think at least, even if you couldn't take the thing and execute it directly, if you at least have everything kind of documented how you got there, and you have all the code and you have kind of the history of the experiments, that would be a starting point. So hopefully that answers your question.
Good. Yeah, I think it does. Is there anyone else who wants to ask a question? We can go ahead and just raise your hand. I'll try to unmute you. If not, we'll give it a couple minutes. If not, we'll turn it over back to Jeff for wrapping things up for the evening. Oh, there is another question. If you see in the Q&A app, Jeff, it looks like the package seems to be broken for Stephen. He installs 131 from pip. He imports it, but the contents are missing. He types import data spaces, and then the dir on data spaces doesn't show him what he expected.
You know what platform this was?
Stephen, let me just go ahead and, Stephen, hands up. Stephen, you're allowed to talk.
Hey, Jeff. Yeah, macOS.
Okay, guys. Let me try it and email you offline. I installed that version today, so
Yeah,
I don't know. Let me poke around and see what might be happening. And are using like, what Python are you using?
I believe 376.
And you're using it through Anaconda or through
Through Anaconda, yeah.
Okay, so let me try it and see if there's anything going on.
Yeah, just a fun.
Anyone else want to raise their hand? Anyone else want to ask a question? We can, if you have a microphone ready, we can unmute you.
This is Karen. I'm going to jump in with a quick question for people who may be beginners in Python and you used Conda to install. And a lot of the early tutorials, so this is like at a much lower level than your talk. Can you talk a little bit about using Conda, especially in the data community, versus using pip to install things?
Sure. Well, I would say, so I tend to use Conda these days, but that's more, so the difference with Conda is that the Conda packager can install binary files kind of more directly. It's a little more flexible. It's not quite as Python focused. So it's a little more powerful than what pip can do. So for some of the things, it can work out a little better, and you may not need, like at least it used to be in the old days when I was installing using the virtual M's and pip on Linux. Then you end up, it's easier sometimes to just go and install, like you have to install an OS level package and then install things. And so I think if you're in the data science world and you're doing a lot of these things that are, requiring kind of complicated binaries, then it's good for that. And, but I think it's partly, I think you could probably get any of these stacks working in either one. And certainly my tool is not specific. And if you looked at my environment file, which is kind of like the requirements.txt that you would have for pip, is also has some pip dependencies too. So it, hopefully that answers your question.
Yeah, that's great. Thanks.
Are there any more questions? We can turn questions back over. We can, if you raise your hand, you can ask the questions live. All right, Jeff, I'm going to go ahead and turn it back over. Oh, there's one more question. David just asked one. If no one else has a question, it would be interesting to hear Jeff say a little bit about the magics he mentioned in Jupyter.
Oh, okay. That was a very painful experience, let me tell you. So the magics, is basically, magics are kind of specialized commands you can add. And there's a bunch of them that come out of the box. And basically a magic typically, so you call it from the notebook, and then, but it's running in the kernel, which is basically a Python interpreter, which might or might not be on the same machine. And so, there's an asynchronous protocol using 0MQ, if you've heard of that before, going on between the browser and the IPY kernel, it's called, which is the Python running on the server. And so, in my case, if you're doing something simple, like you just want to print something out or whatever, some simple ones are pretty easy to implement. But they can get more complicated if, like when I took the snapshot, basically I'm calling some undocumented API in the Jupyter notebook on the JavaScript side to tell it to save the notebook. And then I have to kind of do some stuff going back and forth. And when the notebook's saved, then I can actually take the snapshot. Supposedly Jupyter Lab, it kind of has better APIs, but it's also completely different APIs, and it's using Angular and a bunch of completely different stack. So, which is unfortunate. But but the magics. So some magics will work depending on how complicated they are. They work with both Jupyter Notebook and Lab. In my case, they only work with the Jupyter Notebook because of what I'm trying to do. They don't have the same APIs in Jupyter Lab. So hopefully that answers that.
Yeah. Hey, Jeff, you see that there's one more question. You might want to type it live. There's a box for type answer instead of speaking. But
Okay.
The question is, what is the package URL? If you have that handy, we can put that in there. If not, we can follow up with
It's
it.
actually, can you see my monitor? So
We can, yeah.
Well, so it's right. So I don't know by
Perfect. Answer
right.
live. Go ahead.
Well, so here, if you want the pip one, so there's the website. Okay, wait. Oops, the question. Just, I guess I found it out. But right here, this is the pip package URL. This is the URL of the website, which kind of points to everything else.
Perfect. Any last questions? Any last raised hands before we turn it back over to Jeff as the organizer, not Jeff as the speaker? All right, Jeff, all yours.
Okay, well, I guess thanks a lot, everyone, for attending our first online meeting. I think, we'll kind of get the hang of how these work. Hopefully we don't have to do too many more, and we'll get to see you in person. But I appreciate everyone tuning in, both for my talk and the other talks. And if you're interested in talking in upcoming months, let us know. We're going to kind of rebuild our speaker schedule now, I think. So thanks a lot. I don't know, Glenn.